So I'm going to talk about lossless data compression. I'm going to give you a practical example to see how it works and what's the concept of entropy and what it exactly gives us. So data compression is the art of reducing the number of bits that represent an information source or thank you, or to store or to transmit data. So this compression can be either lossless or lossy. So so if you compress an information source losslessly, then it can be decompressed at a later time, so that no information will be lost. Okay, so an example is the Morse code, and the lossy compression, it throws out the unimportant data, and it only takes into account the data which is important to us. An example is the National Television System Committee, which it was a standard which was useful up until 2009, and it was kind of the concept was they were ignoring let's say the colors which was not sensitive to the human eye. So so I probably skip a couple of these lines here because Michael introduced the concept of entropy. So entropy is basically a measure of uncertainty, and the lower bound which gives you an on the expected compression limit or ratio. So it gives you the expected limit to which you can compress your data. So mathematically speaking, this is the definition of the entropy of an information source. So information source is kind of shown by this x, which is a random variable, and this is the definition where P of I is the probability that the ice character or ice symbol appear. So if the base of this logarithm is 2, then the unit of this entropy is going to be bits or Shannon. If b is the natural number, I mean the Neper number, then this logarithm is the natural logarithm, and the entropy unit is nats. And if b equals 10, then the unit is Hartley. So this is the basic theorem, which is the Shannon's source coding theorem. So Shannon himself introduced the concept of entropy, and he also gave this lower bound on the limit of compressed ratio. So if you have n identically and independently distributed random variables, then and if the entropy of that is h of x, then you can compress that information into more than n times h of x, which is the entropy. And the converse is also true, meaning if you compress into fewer than n times the entropy, then certainly you will lose in the decompression. So I'm going to give you an example here. So suppose that you want to compress pi, the number pi in mathematics, the digits of that is 3, 1, 4, and assume that the character appear equally probable. So here I give you two tables. So the characters are 0 to 9. The probability of appearing one character is 0.1 because there are 10 of them, so it's uniformly distributed. And if I show the binary code associated to this, which is a naive way of representing these characters, so I'm going to have like 10 of these binary code words of length 4. So if you find the average compression ratio, it's going to be 10 times 4 because I have 10 of these symbols, each of length 4, and the compression ratio is going to be 4 bits per character. Later on, Huffman introduced its code, which is called Huffman code, And he could reduce the number of bits which can represent, let's say, a couple of these characters. Let's say the first six characters are now represented by code words of length 3, but the others are represented by code words of length 4. And hence, the average compression code length is going to be, so I have 6 of them which are length 3, and 4 of them which are of length 4. And hence, the average compression length is 3.4 bits per character. So as you can see, I have reduced from 4 bits to 3.4. Now, what is the limit? How can I go further down? So that's the entropy. So the entropy is the limit that you can go up to that point. So let's compute the entropy. So based on the definition, we had like 10 characters, 0 to 9. And if you plug in these probabilities, 0.1 into the definition of the entropy, you will get 3.3. So as you can see, we got pretty close to the Shannon's entropy, which is the lower limit of the compression ratio limit. So it started with binary code, which was 4.0 bits per character. We introduced Huffman, which is 3.4, and the limit is 3.3. So just to note that this Huffman coding is being developed by Lempel and Ziv later on in '77, and later on with Lempel, Ziv, and Walsh. And these algorithms are being used in day-to-day life, like when you compress the button to let's say, zip something, or this WinZip is using this Huffman along with another algorithm, or even gzip or rar, or all these applications in computer using these algorithms of Huffman, a developed algorithm based on the Huffman. So that's pretty much what I wanted to say. Thank you.